Hear me out. Donuts make me a functioning adult. See, I usually have a rage-induced meltdown when the squat rack at the gym is occupied, but then I started telling myself I could have a donut if I took deep, calming breaths and walked away from the rack without screaming at someone. Now, you might not believe in the magical power of the donut, but statistics has specific ways for us to compare things like my habits pre-donut and post-donut. Like, say, across the city right now, there's a doctor trying to come up with a new drug that helps lower systolic blood pressure. We'll call this hero doc, and she's hard at work comparing two groups. But this isn't like the statistical test that we're used to, because here she's comparing groups that are dependent. Hi, I'm Sabrina Cruz, and this is Study Hall, Real-World Statistics. We learned in our episode on independent samples t-test that we can compare two different groups of things, but those tests only work well if the samples are, well, independent. There's lots of situations where we have groups that we want to compare, but they're actually dependent. Like my gym rage tendencies before a mouth-watering reward encourages me to calm down is related to my gym behavior after, just due to the fact that I'm, well, me either way. Two groups can be related even if it isn't a before and after situation. Like if we wanted to study the effect of going to different colleges on twins. No matter what though, there's always going to be some relationship between the two groups being studied, but we don't know what's going on within each of these groups. Which brings us to a test known by many names: the paired t-test, the matched paired t-test, or sometimes just a dependent t-test. Deciding which phrase to use really depends on things like your field of study. What matters more is what they do. Let's get back to our hero doc. To get a baseline for her test, she takes the blood pressure of a bunch of patients before they start an experimental treatment. Doc follows those same patients over the course of the treatment. They take the medication for a week and return to get their blood pressure measured again, so Doc can see if, on average, blood pressures are going down. Doc now has two groups, the patients before taking the drug and after taking the drug. But even though each individual person is independent of one another, they are not independent between before and after measurements. Remember, they're the same patients. And that impacts what counts as the sample size. Doc has collected 100 measurements, 2 for each of her 50 patients, but she really only has 50 pairs represented in her sample, so that's the relevant sample size. And what Doc is interested in isn't the before measurements or the after measurements, it's the difference the medication made. So what she needs to analyze is the mean difference. Basically, she's taking an average, but not of the raw data. Because Doc wants to understand the typical difference in blood pressure before and after the treatment, she first takes the differences in blood pressure measurements at the patient level, or the before number minus the after number, and then takes the average. What Doc is doing is different from taking the difference between means. That would mean taking the average of the before group's blood pressure measurements and the average of the after group's blood pressure measurements, and then taking the difference between those two numbers. Now, Doc has collected all the information she needs, but what if, in a wacky hypothetical world, I'm suddenly called in to help her decide if this possible miracle medicine is working? She wants my math skills, okay? I'll need the same elements as usual for a hypothesis test. Hypotheses, assumptions to check, a test statistic, and a probability distribution to give us our p-value so that we can make a final decision. Luckily, this paired t-test has a lot in common with other tests we've seen before. I'll start by assuming the null hypothesis, which is that the drug doesn't work, while my alternative hypothesis is that it does. Under the null hypothesis, when I subtract people's blood pressure after they take the medication from their blood pressure before they take it, I get 0, no change. So in stats terms, we'd say that the true mean difference under the null hypothesis is 0. But in my alternative hypothesis, I get a positive number, because after the treatment, people have lower blood pressure if the drug works. Now, there's more than 30 pairs because Doc measured 50 people. That means that there is a large enough sample size for the central limit theorem to kick in. So we're on to the test statistic, which tells us how many standard deviations away our observed difference in blood pressures is from the hypothesized mean difference. To get the test statistic, we need to do some math. We know that we want to take all the blood pressure differences, subtracting people's after blood pressures from their before blood pressures, and then take the mean of those differences. Again, in stats terms, the numerator is the observed value of interest, which here is the mean difference that we just calculated, minus what we expect the difference to be if the null hypothesis is true. And here, that number is 0, representing no effect of the treatment. In Doc's case, the mean difference is 8.2, making that our observed value. According to the null hypothesis, hypothesis, that difference would be 0, so we subtract 0 from 8.2. Now that the numerator's dealt with, we're faced with the pesky denominator. The denominator measures variability. Since we want to know how much the differences in blood pressure measurements vary across individuals, we look at the standard deviation of all the differences in blood pressure values. We don't know the true population version, though. That would mean having access to everyone in the world's before and after blood pressure measurements. But we can estimate that variability using the sample standard deviation of all the blood pressure differences. Doc already calculated that for us. It's 4.5. We also know that the relevant sample size is the number of pairs, not the total number of measurements, so that's 50. Putting it all together, we have a test statistic of 12.89. We're still working with a t-distribution here because we had to estimate the variability in the denominator rather than knowing the population version. And in this case, our degrees of freedom is the sample size -1, leaving us with 49. Now it's time for our favorite measurement that shows us the chances of obtaining our observed results if the null hypothesis is true. That's right, folks. P-value time. Looking at our handy chart, there's no row for 49 degrees of freedom, so we're stuck down a row at 30. We'll stick to our standard 0.05 significance level, which gives us a 1.697 critical value. Now again, we should draw a picture. If the area to the right of 1.697 is 0.05, then the area to the right of our test statistic, 12.89, is way smaller. That really small area represents our p-value, so that's enough evidence to reject the null hypothesis in favor of the alternative hypothesis. That's really good news. It means Doc's found an effective drug. And if she can do that without a donut, imagine what she could do with one. Now, we just looked at a one-sided test because we expected the drug to decrease blood pressure if it worked at all. But if we don't have a good sense for what direction the treatment effect will take, there are also two-sided dependent t-tests, like if there was some parallel universe out there where the drug actually increased blood pressure. In a two-sided test, we change the alternative hypothesis to be not equal rather than less than or greater than. We'd also cut our significance level in half before looking at the t-table. We do that because the table only shows the area to the right of a significance level, but we're going to want the area to the right and left. But thanks to the symmetry of the t-distribution, we know that the area to the right of a value is the same as the area to the left of the negative version of that value. And if we want to offload all of that work onto the computer, we can also use software. With the before data in one column and the after data in another, we can use our software's t-test function to calculate the test statistic and p-value for us. We will just need to specify that the data is paired. The computer can't read our minds yet, and whether we're doing a one- or two-sided test. Still, depending on the context, it might not be enough to know that a difference does exist. We might want to measure the magnitude of that difference. Like how much my gym rage calms down could vary widely between a scenario where I am completely calm thanks to a motivating donut versus a donut inspiring me to just be a teensy bit less likely to die of fury. That's even though both of those scenarios may contain real differences from my natural no-donut state. Thankfully, we have a way to do that. Cohen's D measures a difference or effect size in a standardized way. That difference itself can represent the mean difference between things like blood pressure measurements before and after treatment, or levels of rage with or without a donut as an incentive to be patient with gym bros. Cohen's D is calculated first by taking either mean difference or difference between means, depending on whether you're looking at dependent or independent samples, and then dividing by the relevant standard deviation. So it's almost the test statistic, but it doesn't have any additional scaling by the sample size. This standardized effect size can help us understand if something is just statistically significant, where we've rejected a null hypothesis, or if it's also practically significant, and the detective difference is big enough that it is meaningful to us in some way. Like, even though Doc found that her blood pressure medicine's effect is statistically significant, let's say that the drop in blood pressure was too small to make a noticeable difference in a person's quality of life. In that case, we might decide it wasn't worth the cost or possible negative side effects. We can find out whether it seems worth it using Cohen's D. For Doc's research on blood pressure, the effect size is 8.2 divided by 4.5, which is about 1.82. This number represents the mean difference between blood pressure with treatment and blood pressure with no treatment, using units of standard deviation of all the measured differences. Looking at the number helps us understand whether or not the effect is large when compared to the typical variation in the data overall. Now, that 1.82 is pretty big by Cohen's D standard, but whether or not that value is enough really depends. Like, if we already have blood pressure that is kind of elevated but close to normal levels, the drug might not feel worth it. But for someone dealing with hypertension, that effect size may be enough to do the trick. Taking a step back, though, the real thing to remember is that differences are important. They're all around us, and uncovering them can be key for everything from motivating you to do chores to making critical discoveries. That means understanding changes before and after something happens, but it also includes just about any difference, even involving dependent groups, like curing diseases, or just me at the gym reminding myself not to scream because there's a delicious, jelly-filled disc waiting in my locker. If you're enjoying this series and are interested in taking the full Study Hall Real-World Statistics course and earning college credit from ASU, check out gostudyhall.com or click on the button to learn more. And if you want to help us out, give this video a like, smash that subscribe button, and comment your reason for not giving in to rage. Thanks for watching, and see you next time.